in this hour we will talk about power factor correction. Okay, and by correction we basically mean increasing. Okay, so first we'll see why does power factor need to be increased, and then we will talk about ways to increase it. Okay, so let's begin by considering the following simple scenario. Consider the following situation. Okay, where we have a generator, okay, that produces power, electrical power, and then through transmission lines it's transferred to the customer. Okay, this is the RMS value of the voltage. Here we have RL indicating or representing the resistance of the transmission lines, and this is our generator. Okay, and this end we can call it the customer. Okay, possibly an industrial establishment, and it's operating at some power factor. Okay, cosine phi, let's say. Now, in general, the customer, the industrial establishment that we mentioned, requires voltage at some specified rate. Okay, let's say 220 volts RMS. So in general, the customer requires power at a specified voltage. Okay. Furthermore, if this is an industrial establishment, as we said, the energy requirement will take place at a constant rate. Okay, therefore the power associated to this load or the customer or the average power would be more or less constant. Hence, we can take both the voltage and the power absorbed by the load constant. By power I mean the average power. Okay, hence let us take the load voltage V RMS and the average power delivered to the load, which we denote by P sub L as fixed. Okay. Now, under these assumptions, which are realistic, we will now try to figure out the power loss through the transmission lines and its relation to the power factor of the customer. Okay, here R sub L is the impedance, okay, of the transmission lines. Now, usually transmission lines are very good conductors, but because the power is generated and used at too far away from the geographical point of view locations, the transmission lines cover very large distances. So even though they're very good conductors, they have to be in a realistic model. They have to have some non-zero impedance. Okay, that's why we have this RL here instead of just a straight line. So what we have is the following: PL, the power requirement of the customer, which we assume to be fixed, equals IRMS times VRMS times the power factor, okay? And this is the RMS value of the current flowing through the transmission lines and then entering to the load. This IRMS times VRMS, VRMS is the voltage at the customer side, is the apparent power times cosine phi, or the power factor, is the real part of the complex power, which is the average power, okay, delivered to the load. Therefore, IRMS equals the effective value of the current equals the power divided by VRMS times the power factor. And then that value, that current squared times the real part of the impedance, or RL, of the transmission lines, would give us the power that's lost during transmission. Okay, so power lost during transmission is P loss equals I RMS squared times the resistance of the transmission lines, RL. And that, in terms of the power, load power, and the power factor, reads V RMS times PF square times RL. Let's call this equation 1. So power loss during transmission equals this expression. Now let's interpret equation 1, which is easy to do. Note that we cannot play under realistic assumptions or conditions. We cannot play with PL and VRMS. Okay, this is the power consumed by the customer. This is the voltage, which has to be fixed because customer requires voltage at some specified rate. And also we cannot do much about this thing, okay, RL. It has to do with some inherent property of the metals used in transmission lines, okay. Therefore, the only thing that we perhaps play with seems to be this power factor at the load. And if you look at equation 1, we see that if power factor is small, okay, if it's, for instance, something close to 0, the denominator becomes small, and in turn the RMS value of the current increases. As a result of that large current travels through the transmission lines, there will be much loss, okay, during transmission lines. On the other hand, if somehow power factor is very large, and remember that it's cosine of something, therefore it can be as large, maximum, the largest value that it can take is 1. So if power factor is very, very close to 1, so that's, in that case, the loss through the transmission would be as small as possible. Therefore, in an ideal case, what we want the power factor to be as close to 1 as possible in order to reduce the loss during transmission. So let's put that observation down. The smaller the power factor, the larger the loss during transmission, and we don't want that. Therefore, the larger the power factor, in other words, if we can make it approximately 1, as close to 1 as possible, the better it is. Okay. So we will burn less coal, let's say, at the plant that's generating power, that's feeding the city nearby. Okay, so that's the motivation behind the fact that power factor, if possible, should be increased. Okay. Now, in industrial applications, the power factor of loads, okay, are usually lagging. Okay, is usually lagging, and the reason for that is in industrial applications there are many electric motors, okay, that are doing some work, and electrical motors, they have windings, therefore they are in a sense inductive equipment. Okay, so that being the case, the inductors or the inductive effects will be dominating the capacitive effects, and if you do nothing about it, the power factor of loads will be lagging due to the windings of the electric motors. Okay, and a common way to increase the power factor is therefore introduce some capacitive effect, and that can be done clearly by a capacitor. It's therefore to connect a parallel capacitor to the load. Okay, so here is the situation after power correction. Still we have here the generator. This is the transmission line RL, and here we have the load with power factor lagging due to the windings of the motors, let's say. Okay, so what we do is we connect to the load in parallel a capacitor, okay, to decrease the total power. Okay, therefore increase the power factor, and by doing so increase the power factor of the overall load seen by the generator system. Okay, now let's apply this idea to an example. Okay, which reads as follows. We have a generator that supplies two parallel loads at a fixed voltage, effective voltage of 220 volts RMS with frequency 50 hertz, and with a net or effective power factor of 3/4 lagging. Now one of the loads has 4800 volt amp rating at the power factor of 0.85, and it's lagging. Okay. And as for the second load, it absorbs 4 kilowatts of real power. Okay, average power. Okay, for this situation, we are asked to perform the following computations. What are the apparent power, and the power factor of the second load? Okay, and then the second part has to do with power factor correction. What we're asked to do is we're asked to raise that power factor, the net power factor of 0.75 to 0.95, so that make it much closer to 1. Determine the kilovolt amp reactive rating. Okay, so we're asked for the reactive power and the capacitance value of the capacitor that should be connected okay. So we're talking about this capacitor here, which we will connect to our two loads that are in parallel. Connected in parallel with the two loads to increase the net power factor to 0.95 lagging. Okay, so let's start from the first part. And when we're dealing with such power problems, it's almost always a good idea to have a simple sketch of the generator, the load, the transmission line, to see the general picture in a more visual way. Okay. Okay, so here goes the solution. We have the generator that produces 220 volt RMS. So this is a slightly new notation that we are introducing here. This VRMS is a new unit, okay? It's like volts, but it's volt with subscript RMS. It means that whatever the voltage here is, and we're talking about the circuit in sinusoidal steady state. So here we have a sinusoidal signal, and the amplitude of that voltage is this thing times square root of 2, or the RMS value of whatever that voltage is, 220 volts. Okay, so to communicate that information, people simply write things like that, plus minus the polarity, and in between they indicate the RMS value of the voltage. Okay, now this generator is connected to two customers, let's say, or two loads. Okay, suppose that the first one is Z1, the second impedance is Z2. Okay, and as far as the generator or the source is concerned, so it will see some effective impedance here, some effective load, and the power factor of that load, okay, seen by the source is 0.75 lagging. Okay, so here the power factor, net power factor, reads 0.75 lagging. Okay, so the overall load is seen as an inductive load by the source. Okay, so let's write down what we're given. So we are given that load 1 has the power factor of 0.85. Okay, 0.85, and it's lagging. Okay, now therefore sine of phi 1 could either have two, could either be positive or negative, but due to this word lagging, we know that it has to be positive. So sine of phi 1 is positive since the power factor is lagging, or since the load is inductive. Okay, and therefore we can immediately write S1 to equal. Now the other piece of information that we're given is the rating, or the volt amp rating of the first load. So by looking at the unit, we know that this number denotes this quantity represents the apparent power of that load. Okay, so this is the magnitude of our complex power. Hence, the complex power can be written as that magnitude times cosine phi 1 plus j sine phi 1. Cosine phi 1 is the power factor by definition, and sine phi 1 is 1 minus this square, and then you take the square root, and you have to determine the sign, and the sign is positive because the power factor is lagging. In other words, S1 equals 0.85 plus, okay, plus because it's lagging, j times sine of phi 1, which is 1 minus 0.85 square, and then you take the square root. And that can be computed to equal approximately 4080 plus j 2530 volt amps. So that's the complex power of the first load. How about load 2? Load 2. As for load 2, the only piece of information we're given is that the average power is 4000 watts, okay, or the real part of its complex power is 4000 watts. We're not given the power factor directly for the second load, but we are given the net power factor seen by the source. Therefore, that information combined with the power rating of second load plus the complex power of the first load should be enough to figure out all the real and complex powers for all the loads. So load 2, whose complex power we denote by S2, equals 4000. So that's the real part of the complex power, which is the average power given as 4000 watts, plus J times the reactive power for the second load. Now the total complex power delivered by the source to the combination of load 1 and load 2 due to conservation of power simply is S1 plus S2. Okay, S equals S1 plus S2, and that we can write as Okay, 80 plus J 2530 plus Q2, okay, volt amps. And this is the overall reactive power that's delivered to or consumed by the total load. Now, for this S, okay, the complex power delivered to the combination, the associated power factor is 0.75 because that's the net power factor. Okay, so for this S, the power factor is 0.75 lagging. Okay, let's quickly draw the power triangle. Which will simplify certain things for us to see better. Okay, so this is the power triangle representing the overall load. This is the phase phi, whose cosine is 0.75. This is our Q, and this is the real power, okay, the average power delivered to the loads. Okay, so what we know is cosine 5 equals 3 over 4, okay, 0.75. And since it's lagging, we draw the vertical side representing the reactive power pointing up by convention. Hence, Q equals this side times the tangent of this phi. Okay, and that's tangent of arc cos 0.75, and that's times over 3. Okay, and then that produces the reactive power, which reads approximately 7,125. The unit must be volt amp reactive. Okay, so that's the overall reactive power associated to this connection of loads, and that must equal, by conservation of power, this plus that, and from there we can figure out Q2. 5 equals 2530 plus Q2, which yields Q2 equals 4595 volt amp reactive. Okay, now we know everything regarding the second load. We know its real power, we know its reactive power, and once those two things are known, we know everything: the power factor, the complex power, and so on. Hence, S2, the complex power for the second load, reads 4000 plus J 4595 volt amps. So we were asked for the apparent power for the second load, and by definition apparent power is the magnitude of this complex number, the complex power. Hence, apparent power equals approximately 6090 volt amps. Okay, as for the power factor of the second load, since we have the triangle, we can easily compute the cosine of the phase of the second load, phi 2. This side is 4000 watts, so that's representing the real power. The vertical side, which we draw upward because Q2 turned out to be positive. Okay, positive means upward, negative means downward. So that's 4595 volt amp reactive, and hypotenuse represents the apparent power, which is this number here, 6090 volt amps. Okay, so cosine phi 2 is 4000 over the hypotenuse 6090, which is about 0.66. Therefore, the power factor for the second load is 2/3. Whether it's lagging or leading, to determine that, you look at the sign of the reactive power. Since the sign of the reactive power is positive, it's a lagging power factor. So therefore, second load is also an inductive load. Okay, now we're ready for the second part of the question, where we will now introduce a third, in a sense, third component, which will be a capacitor connected in parallel with the combination Z1 and Z2. Load 1, and then here we have load 2. Plus minus 220 volt RMS, and the frequency is 50 Hertz. Let's call this voltage V. Okay, this is the voltage phasor whose RMS value or effective value we know equals 220. This is the capacitor, okay, and here we have Z1 and Z2. Okay, so okay, well, these are impedances. Therefore, to be more grammatically correct, let's write this also as impedance J omega C, and this omega is the frequency of operation in radians per second, and we're given the frequency in Hertz. Therefore, omega in our case is this times 2 pi, which is 100 pi radians per second. Okay, now, let the power of C, our capacitor, be S3, okay, which is the real part plus the imaginary part, okay, JQ3. Now we know that capacitor, also an inductor, will always have zero average power. Therefore, S3, the complex power, is purely imaginary, which is JQ3. Moreover, we know that Q3, since it's the reactive power of a capacitor, has to be negative. Okay, we know that. The average power of the capacitor equals 0, and the reactive power is negative. Then the new total complex power becomes, okay, S nu. Now this S nu is the new complex power delivered by the source to this combination of 3 pieces. One of those pieces is our capacitor, and then we have the 2 loads that we had in the original problem. Okay, and we can call this the third load, Z3. Okay, now S new equals S1 plus S2 plus S3. Note that in the new situation, the S1 and S2 haven't changed because the voltage here is fixed. So they still see the same voltage drop from the RMS point of view across their terminals. Therefore, everything is the same for Z1 and Z2, okay, from the power point of view at least. And then S new equals S1 plus S2 plus S3. S1 and S2 we already computed, and we just said that they're the same for the new situation. So we can write this to equal plus J. Okay, so this was the previously computed reactive power, 7125. To that we now add a third term plus Q3. Okay, now the aim is, since Q3 is negative, by choosing the capacitance value so that make this thing as small as possible, or in our case make it equal to 0.95. No, not 0.95, but the cosine will be 0.95. Make this thing small so that the this part will be large relative to the imaginary part, which would increase the cosine of the phase. Okay, so let's draw the new triangle, power triangle. So this is the new triangle with hopefully a much smaller vertical side, because vertical side represents the reactive power. Okay, this is 880. Note that the real part of the total complex power hasn't changed because the capacitor has no real power or average power contribution to the overall complex power. So this, the horizontal side hasn't changed, but the vertical side we're hoping to get smaller. 7125 plus the reactive power of the capacitor. And this angle here is, let's call it phi nu, cosine of which is our new power factor, which we want to equal 0.95. Okay, so this is what we want. What we want is cosine phi nu equals 0.95. Okay, a value that's much closer to 1 compared to the original value without the capacitor. So 7125 plus Q3, this is our new reactive power, divided by the horizontal side, equals the tangent of our new phase. Equals tangent of new phase, and the new phase is arc cos 0.95. Okay, this can be computed to equal 2655. Okay, hence Q3, the reactive power associated to our capacitor, reads minus 4470 volt amp R. So that's the volt amp R var rating of our capacitor. Okay, so what we have therefore is S3 equals P3 plus JQ3. P3 is 0 because we're talking about a capacitor, and Q3 is minus 4470. So therefore S3 is minus J 4470 volt amps. Okay. Now S3 equals the effective value of the current squared times the So I made a mistake here. Excuse me. So I have to make this, of course, 1 over j omega c. Okay, so that's RG3. Okay. So the okay, S3 is the effective value of the current squared times the impedance Z3, or since instead of the current we know the voltage, effective value of the voltage squared divided by the impedance conjugate, okay, Z3 star. So let's therefore write S3 as V effective square over Z3 conjugate. And that equals V effective square 1 over j omega c was RZ3, but now we have this conjugation, therefore we have to put a minus sign in front of j. And that reads minus j omega c times the square of the effective value of the voltage V, which is 220. Okay, so that equals minus j 4470. Hence, omega c V effective square equals 4470. Okay. Now we know omega, which is 50, the frequency in hertz, times 2 pi, because omega is measured in radians per second. We know V effective, which is 220. Therefore, the only thing that's unknown here is the capacitance. Okay, so let's quickly compute that and we'll be done. So V effective equals 220 volts, omega equals 2 pi f. F is given to be 50 hertz, so that makes 314 radians per second, approximately. Therefore, we can write C equals 4470, which is the magnitude of the reactive power of the capacitor Q3, divided by 100 pi times 220 square. And that equals 200 approximately 94 times 10 to the minus 6 farads. Hence, the capacitance of the capacitor to be connected in parallel with the first two loads, Z1 and Z2, in order to increase the power factor from 0.75 to 0.95 equals 294 microfarads. Okay. So, before we close this lecture, let's also talk about, like power factor correction, another practically important concept, and that's the concept of efficiency. Okay, so let's define what we mean by efficiency in this context, and then we'll talk about ways to increase it. Okay, now here is our example of on efficiency, and let me draw the circuit for this example, and then let's define efficiency over that circuit. So this circuit represents a general situation. We have the generator where the electricity is produced. Okay, so that the power plant, we're representing it by a simple voltage, independent voltage source. And then we have the transmission lines, which is represented by some resistance, RL. And at the other end of the transmission lines, in the city, let's say, we have the customer or the industrial establishment. And that's represented by some impedance, ZL. Okay, for this problem, we're told that this voltage, the effective value of the voltage is 250 here. Okay, so that's 250 VRMS. We're using our new units, volt RMS units, which means that the effective value of the voltage appears here is 250 volts. RL is given to be 1 ohm. Okay, and ZL is given to be 7 plus J6 ohms. Now, by efficiency, we mean the following. Okay, or percent efficiency. Okay, usually it's noted by the Greek letter eta. The percent efficiency is simply the power, the real power generated, the ratio of the real power consumed by load divided by the real power generated at the plant or at the source. Okay, so the real power absorbed by load over real power supplied by the source. Okay, since we have the adjective percent in front, we multiply this number by 100%. Okay, so that's efficiency definition. Now, ideally, we would want, or we expect this to be 100, but due to the loss, which is not always negligible, loss during transmission, the power, not all power generated here reaches the load. Some will be shared, some will be lost during transmission or by the transmission lines. Okay, now for this case, for the numerical values given, let's apply this definition to this situation, figure out the efficiency, and then once we have that efficiency, we can talk about ways to increase it, okay, to make it as close to 100% as possible. Okay, so Z equivalent equals, so this is the effective or the equivalent impedance seen by the source. It's simply this impedance line, transmission line resistance plus, or the impedance plus the impedance of the load. So that makes 8 plus J6 ohms. Okay, let's call the current passing through the transmission lines and then entering the load I. Okay. Now we can easily compute the effective value of the current. I RMS equals the RMS value of the voltage of the source divided by the magnitude of the impedance. Okay, Z equivalent. And that reads, the magnitude of this impedance is 10, therefore 250 divided by 10, we're talking about a 25 amp current passing through our transmission lines. Okay, once we have the current, we can easily compute the average powers consumed by the transmission line and the load. PL, okay, the average power consumed by the load is the real part of the load impedance, which is 7 multiplied by the square of the effective value of the current. So PL reads 7 times I RMS square. And likewise, PL reads the resistance 1 times RMS square. This produces 4375 watts, and the power lost during transmission is simply 25 square watts. Okay, now we have the power of the load, power lost during transmission. Hence, we can use that definition to compute eta as PL divided by PL plus P lowercase l times 100%. Okay, so that equals 4375 divided by 4375 plus 625, which is 4375 over 5,000. Okay, and expressed in percentage, that's 75.5%. Okay, so that's the efficiency of this system for the given parameter values. Now this looks like high, but it isn't from the real operation point of view. It can be made much higher. Okay, and it should be made much higher because it's quite a loss. We're losing 12.5% of the power during transmission. Okay, so that's very, very high. So what's being done to reduce that loss or increase the efficiency is reducing the current, okay, that's passing through the transmission lines, and that can be done without affecting the overall power much by using transformers. Okay. Now consider the following correction, if you will, to the efficiency. Now consider the following. Here we have the plant or the source as before, producing 250 volts. And instead of connecting this voltage directly to the transmission lines, what we do is we raise it first by some amount, okay? Let's say by an amount of 10. Well, in practical applications, it's much, much higher than 1 to 10. But for simplicity, let's make this voltage from 250 volts to 2500 volts, okay, by using the following transformer. And then the power is now transmitted through the transmission lines at a much higher voltage, okay, 2500 volts. This is RL, which is 1 still, and then once we reach the city, once we reach the customer end, we have to reduce this voltage back to its original value because the customer requires voltage at some fixed rate, okay, and that rate is, let's say, around 250. So we have to reduce this voltage, which is at 2500, back to 250. Okay, so we again use the transformer this time to do the opposite thing. Okay, ZL is 7 plus J6 ohms, and RL as before was 1 ohm. Okay, now the difference between this is also 1:10 to 1. Okay, now the difference between this situation and the original situation is that now the current passing through the transmission lines is not the same current that passes through the load. Okay, so therefore we have to make clear the difference. We're denoting this by I sub lowercase l, and this is I sub uppercase capital L. Okay, now let's compute the efficiency for this new situation. As far as the transmission line is concerned, okay, so this is 1 ohm, remember. As far as the transmission line is concerned, this can be represented by the following equivalent circuit. Okay. Okay, seen from the eyes of the transmission line, RL. RL, which is 1 ohm. And here we have IL. Now this can be represented by just a single voltage source with voltage, okay, 250 times 10, because the voltage ratio is 1 to 10. So here we have N times 250, and N is 10 in our case, so we're talking about 2500 volt RMS. And we do the same thing here. We replace this by a single or the equivalent impedance seen by RL, and that's, we have derived this in one of our previous lectures, square of the turns ratio times the impedance. So we have N square ZL, okay, which is N is 10, ZL is 7 plus J6, so we're talking about 700 plus J600 ohms. Okay, now considering this simpler circuit, we can now easily compute IL. Once we have IL, using the terminal equation, we can compute I capital L, okay? And then once we have IL and I capital L, line current and the load current, we can easily compute the powers. Power for IL and power for ZL, the average power. And once we have the powers, we can apply the efficiency definition and obtain the new efficiency and compare it to the original one. Okay, so by looking at that equivalent circuit, IL effective equals effective value of the voltage, the source voltage 2500 divided by the magnitude of the impedance seen by this source here, which is 1 plus that large impedance 700 plus J600. So that's 2500 divided by 701 plus J600 magnitude, and that's something quite small compared to the previous 25 amps. Now we have only 2.7 amps. Once we have IL, or the line current, we can easily compute the load current by using the terminal equation for the transformer, which reads, okay, N times IL RMS. N is the turns ratio, and that's 10 in our case, which produces 27.1 amps. Okay, and now with these currents we can compute the powers. Okay, the power loss on the transmission lines equals the resistance of the transmission line times the square of the effective value of the current. And P load is the real part of the impedance or the resistance of the load times effective value of the current squared. Now this reads 7.34 watts, and this reads 38 watts. Okay. Now it's already clear that we will have a very large efficiency. And if you compute that, phi nu, let's say, it's almost 100%. Okay, so it's the loss during transmission now is almost negligible with this technique, and this is why power is transmitted at very high voltages, like close to 500,000 volts. Why? Because the power demand of the customer is more or less constant, and power is current times the voltage. So if you increase the voltage using transformation, you decrease the current, and low current through transmission means low loss, because loss is directly proportional to the square of the current. Now you may say, in our model we used ideal, in quotes, transformers, okay? And in real life it's true, there will be losses also during this raising of the voltage and then lowering it down, okay? So there will be loss. In real life the transformers are not ideal, there will be losses, but those losses are much smaller compared to the losses that we would have had if we hadn't used the transformers, okay, in the first place. So that's why almost always the power is transferred at very high voltages to over long distances.